His name was Gerald Houck, and in 1967 he was nobody. He worked in Bay 7 of Building 290 at North American Aviation's Downey facility, a cavernous sheet metal barn that smelled like cutting fluid and burned insulation. His job title was Materials Integration Engineer 2, which meant he wrote test reports that other people signed. He had a gray desk, a Frieden calculator, and a drafting lamp that flickered. He was 31 years old. North American had the Apollo Command and Service Module contract. 12,000 people worked in Downey. Gerald was employee number 8,447. His supervisor was named Bill Tarrant. Bill's supervisor was named Ed Moss. Ed reported to someone Gerald had never met. The Apollo program cost $25 billion. Gerald made $11,200 a year. Every morning he arrived at 6:45 and signed the logbook. He wore short-sleeved white shirts and kept mechanical pencils in his pocket protector. He did not eat lunch with the propulsion group or the thermal engineers. He ate at his desk. He read test specifications while he ate. In photographs from the era, you can see men like Gerald standing in the back corner of group shots, slightly out of focus. They are holding clipboards. They are not smiling. No one remembers their names. By 1967, Apollo was hemorrhaging schedule. The fire that killed Grissom, White, and Chaffee had forced a comprehensive redesign. Thousands of components were being requalified. Every change triggered reviews. Every review triggered documentation. The paper moved slower than the hardware. Gerald's job was to track one category of parts called fluid system elastomers, rubber seals, gaskets, O-rings. Anywhere propellant, coolant, or pressurized gas touched a joint, there was a seal. The command module had 412 of them. The service module had 709. Each seal had a specification. Each specification referenced a material standard. Each material had a qualified vendor. If you wanted to change a seal, you filed an engineering change request. The ECR went to the Materials Review Board, then to Configuration Control, then to NASA. The process took 11 weeks minimum. Gerald spent most of 1967 reviewing failure reports. The reports came from White Sands, from the altitude chamber at Houston, from thermal vac tests at Downey. Seals cracked during temperature cycling. Seals extruded under pressure. Seals lost compression set. Seals swelled in the wrong propellants. Some failed in vacuum. Some failed in pure oxygen. Some failed for reasons no one understood. Each failure stopped testing. Each stoppage burned money. North American was already over budget. NASA was threatening penalties. The engineers responded the way engineers do. They specified tighter tolerances. They added secondary seals. They required harder durometer compounds. They introduced backup systems. Every solution added weight, cost, and complexity. Gerald read the reports and wrote summaries. He did not offer opinions. Nobody asked for them. The problem was not dramatic. No one died. No rockets exploded on television. The problem was that testing stopped constantly for seal-related anomalies. A pressure test would reach 90% of qualification when a transducer detected a slow leak. Engineers would detank the system, disassemble the joint, inspect the seal, write a report, and start over. 3 weeks lost, then it would happen again somewhere else. By 1968, seal failures had caused 214 unplanned test interruptions across Apollo. Each interruption averaged 19 days of schedule impact. The cost was not always visible. It appeared as extended facility rental at White Sands, overtime for test crews, delayed delivery milestones triggering contract penalties, program-level schedule margin erosion, increased spare part inventories, additional qualification testing for replacement seals. No single failure justified a crisis. Together, they formed a constant drag on the program, like a machine leaking hydraulic fluid from 100 small joints. You could not point to one joint and say, this is the problem. The machine still ran. It just ran slower, hotter, more expensively. NASA's response was systematic. They funded a comprehensive seal development program. They contracted with 3 elastomer manufacturers to develop improved compounds. They established new qualification standards requiring thermal cycling from -250 degrees Fahrenheit to +400 degrees Fahrenheit. They created a seal working group that met monthly. North American bought new test equipment. They hired 2 additional seal engineers. They sent people to conferences. They published internal reports with titles like Elastomer Compatibility in Mixed Oxidizer Environments. All of this made sense. All of it followed procedure. None of it was stupid. But the failures continued. In May 1968, during a thermal vacuum test, an environmental control system seal failed at -190 degrees Fahrenheit. The compound became brittle and fractured. Testing stopped for 12 days. In August, a different seal in the same system leaked during pressure-proof testing. The failure review determined that the seal had been over-torqued during installation, but the specification did not clearly define torque limits. A new procedure was written. The seal was replaced. Testing resumed. In November, a fuel line seal failed during pre-launch checkout at the Cape. The vehicle was drained, the seal inspected. It looked fine. No one knew why it leaked. The seal was replaced. The vehicle was refueled. Testing continued. Gerald read every report. He began to notice something. The failures were not random. They clustered. Gerald kept a notebook. Not official, just a pocket spiral he bought at the drugstore. He started logging seal failures by system, by temperature, by pressure, by installation date. He did this at night after his son was asleep, sitting at the kitchen table under a hanging lamp. By March 1969, the pattern was clear. 92% of seal failures occurred in systems where the sealed joint was required to maintain pressure across a temperature change of more than 200 degrees Fahrenheit within 15 minutes. This was common in Apollo. The spacecraft transitioned from deep cold during coast to intense heating during engine burns. Seals in these environments experienced rapid thermal expansion mismatches. But Gerald noticed something else. The seals themselves were not defective. The compounds were fine. The problem was the groove geometry. The grooves were machined to aerospace tolerances. Extremely tight, extremely precise. The seals fit perfectly at room temperature. But when temperature changed rapidly, the metal expanded or contracted faster than the elastomer. The seal became either overcompressed or undercompressed. Overcompression caused extrusion. Undercompression caused leaks. The standard solution was to tighten tolerances further, which made the problem worse. Gerald realized that the groove geometry specification was too precise. The seals needed more room to move. Instead of a groove machined to plus or minus 0.02 of an inch, the groove should be plus or minus 0.08 thousandths. Instead of a tight fit, a loose fit. This violated qualification logic. Tight tolerances meant better control. Loose tolerances meant variability. Variability meant risk. But elastomers were not rigid parts. They needed compliance. Gerald proposed a solution. Replace the precision machined groove with a groove that used a cheap stamped spacer, a thin metal shim that sat under the seal and allowed controlled axial float. The shim cost 9 cents. It was made from annealed stainless steel, 0.020 inches thick, with a simple radial cut. It did not require precision machining. It did not require qualification testing beyond basic material certification. The shim allowed the seal to self-center during thermal expansion. It absorbed the mismatch. It turned a rigid interface into a compliant one. Gerald wrote a 3-page memo in April 1969. He submitted it through the internal suggestion program. He included test data from his own simple bench tests. He had borrowed a spare seal and a machinist's hot plate and a bucket of dry ice. He showed that a seal in a loose groove with a shim maintained pressure across 300 degrees of delta T without leaking. The memo went to Bill Tarrant. Bill read it and put it in a folder. 6 weeks later, Gerald asked Bill about the memo. Bill said, "Yeah, I passed it up to Ed. I think it's in review." It was not in review. Ed Moss had forwarded it to the SEAL working group. The group met on June 12, 1969. Gerald was not invited. He learned about the meeting later from a colleague. The response was polite and procedural. The working group noted that the proposed shim introduced a new part number, which required a drawing, a specification, vendor qualification, and incoming inspection procedures. The shim would need to be flight certified, which required thermal vac testing, vibration testing, and long-term aging studies. The groove geometry change would require remachining tooling and requalifying every affected seal installation, which was approximately 60 joints per vehicle. The estimated cost to implement the change across the Apollo program was $340,000. The estimated schedule impact was 7 months. The working group concluded that the proposed change did not justify the cost and schedule risk, especially since improved elastomer compounds were already in development and showing promising results in laboratory testing. The memo was filed. Gerald received no formal response. Bill told him, "They looked at it. It's just not the right time." Gerald did not argue. He went back to writing test reports. In July 1969, Apollo 11 landed on the moon. In the photographs, you can see the engineers in the control room. Young men in white shirts and narrow ties, headsets on, looking at consoles. Gerald was not there. He watched on a small black and white television in the break room at Downey. The missions continued. So did the SEAL failures. Between 1969 and 1972, Apollo flew 9 successful lunar missions. The program worked, but behind the successes, the SEAL problem persisted. It migrated. When Apollo ended, NASA began Skylab. Skylab used Apollo hardware, command modules, service modules, fluid systems with the same seals. The SEAL failures continued. They were manageable. They were expensive. Then came Apollo-Soyuz in 1975, then shuttle development. Shuttle was different. Shuttle was reusable. Seals that flew once in Apollo would fly dozens of times in Shuttle. The thermal cycling was worse. The pressure loads were higher. The consequences of failure were more severe. By 1977, Shuttle contractors were reporting the same seal problems Apollo had experienced a decade earlier: leaks during thermal vac, extrusion during pressure proof, failures during installation. NASA funded another seal improvement program. They tested new compounds. They tightened tolerances. In 1978, during a shuttle main engine test at Stennis, a fuel line seal failed catastrophically. The engine was destroyed. No one was injured, but the test stand was damaged. The failure review took 4 months. The conclusion was that the seal had extruded due to thermal shock during engine start transient. The solution was to add a secondary backup seal and a pressure relief port. The redesign cost $6 million and delayed engine qualification by 11 months. Gerald Houck was still working at Downey, now Rockwell International. He had been promoted twice. He was a senior engineer now, working on shuttle tile bonding adhesives. He was 52 years old. He heard about the Stennis failure through internal memos. He did not say anything. In 1981, during the STS-2 launch countdown, a seal in the orbiter's auxiliary power unit leaked hydrazine. The launch was scrubbed. The vehicle was rolled back. The seal was replaced. The launch occurred 3 weeks later. In 1983, a fuel line seal on STS-8 leaked during post-landing servicing. The leak was minor. The seal was replaced. The seal problem had cost NASA, cumulatively, an estimated $400 million across Apollo, Skylab, and Shuttle. Not from single catastrophic failures, but from 10,000 small delays, replacements, redesigns, and schedule losses. It was invisible. It was ongoing. It was normal. In 1984, NASA commissioned an independent review of shuttle fluid system reliability. The review was led by a retired Air Force colonel named Robert Crippen, who had also been an astronaut. The review team included engineers from Aerospace Corporation, Lockheed, and Martin Marietta. They were tasked with identifying systemic risks that were not being adequately managed. One of the team members, a thermal engineer named Sandra Oakes, began reviewing historical failure data. She found a pattern: seal failures clustered in high thermal gradient joints. She found references to old memos, old proposals, old bench tests. She found Gerald Houck's 1969 memo in the archives. She called Gerald in October 1984. Gerald did not remember her at first. She explained who she was. She asked if he still had his notes from the bench tests. He said, "I think so. Maybe in a box in the garage?" She asked if he would be willing to repeat the tests under controlled conditions, with instrumentation. He said, "No, sure." The tests took 2 weeks. They were conducted at Aerospace Corporation's laboratory in El Segundo. Gerald brought his original notebook. The results matched his original findings. Seals in loose grooves with simple shims maintained seal integrity across rapid thermal transients better than seals in precision grooves. The physics were straightforward. Compliance absorbed mismatch. Rigidity amplified it. Sandra Oakes included the findings in the review team's report, delivered to NASA in March 1985. The report recommended implementing the shim modification in high-risk joints across the shuttle fleet. NASA convened a Configuration Control Board meeting in June 1985. The board reviewed the proposal. The estimated implementation cost was now $1.2 million, because the modification would be applied only to critical joints, not all joints. The schedule impact was 4 months. The board approved the change. The modification was incorporated into the shuttle fleet between late 1985 and mid-1986. By then, Challenger had already been lost, not due to seals in fluid lines, but due to a solid rocket booster O-ring that failed in cold temperature. A different problem, but with similar root cause: insufficient compliance in a rigid joint. The fluid line shim modification proceeded quietly. It was not mentioned in press releases. It did not appear in congressional testimony. Over the next 15 years, seal failures in shuttle fluid systems dropped by 73%. The modification saved an estimated $18 million per year in avoided test delays and part replacements. Gerald Houck retired in 1991. He received a certificate of appreciation from Rockwell. The certificate thanked him for 34 years of service. It did not mention seals. In 2003, after the Columbia accident, NASA conducted another comprehensive review of shuttle systems. A junior analyst named Kevin Marsh was assigned to review fluid system modification history. He found documentation of the 1985 shim modification. He traced it back to Sandra Oakes' 1984 report. He traced that back to Gerald Houck's 1969 memo. Kevin was 26. He was curious. He looked up Gerald Houck in the Rockwell alumni database. Gerald was 77, living in Seal Beach, California. Kevin called him in November 2003. Gerald did not remember the details at first. Kevin explained what he had found. Gerald said, "Oh yeah, the shim thing. I thought they never used it." Kevin said, "They did. It's still in use. It probably saved the program tens of millions of dollars." Gerald said, "Huh." In 2005, NASA's headquarters history office began a project to document unheralded contributions to the Space Shuttle program. Gerald was interviewed by a historian named Margaret Weidekamp. The interview lasted 40 minutes. Gerald described the seal problem, the memo, the tests. He spoke plainly. He did not exaggerate. The interview was archived. It was not published. In 2008, Gerald received a letter from NASA Administrator Michael Griffin. The letter thanked him for his contribution to the safety and reliability of human spaceflight. It noted that his insight had influenced the design of seals in the Orion spacecraft, then under development. Gerald framed the letter. He hung it in his garage, next to a photograph of Apollo 11. He died in 2011 at age 85. His obituary in the Orange County Register was 4 paragraphs. It mentioned that he had worked on Apollo and Shuttle. It did not mention SEALs. There is no central database of people like Gerald Houck. The Space Shuttle flew 135 missions over 30 years. It carried more than 350 astronauts. It deployed satellites, built the International Space Station, repaired the Hubble telescope. The program cost over $200 billion. Somewhere in that cost, invisible and uncounted, are the contributions of people who prevented failures no one noticed, who saved money no one tracked, who proposed solutions no one celebrated. They were not engineers with names on patents. They were not managers with corner offices. They were people who read failure reports late at night, who noticed patterns in data no one else looked at, who tested ideas in their garages with borrowed parts. The space shuttle did not succeed because of visionaries. It succeeded because of cheap parts, noticed by people no one listened to, implemented quietly, years too late. Civilizations are held together by 9-cent shims. Most of them are still in boxes and garages, uninstalled.